Good afternoon and welcome to Machining with Solids webinar brought to you by Camco. This afternoon we are going to look at machining with 2.5D solids and how it can benefit you. During the webinar presentation, if you have any questions, enter them into the Q&A window on your webinar dashboard screen. My name is Patrick Mooney and I'm the field engineer for Camco. And today we are going to talk about the advantages of machining with solids. When I go to a customer's facility, most often what I see, even though the customer may have had good training, for whatever reason they have fallen into bad habits and they are not setting up and using solids correctly, therefore they don't use them at all. But they have tremendous benefit. Machining with solids allows us to do a number of things. We can see the part while we're machining it, which makes it much more tangible to us. And also machining with solids, it has a monetary benefit for your company as well. Your time is worth roughly $3 a minute to your company. So every minute that you can save in programming or setting up a program is money that your company is making, and profit is good for everybody. So the steps of machining from a solid, we're going to go through step by step in this presentation. We have several solids that we're going to work with, and we're talking about 2.5D solids rather than three-dimensional solids. Three-dimensional solids would require us to use a ball end mill or maybe a barrel type end mill to do surfacing on surfaces that are not planar to the normal axis of the machine. In other words, the mouse that you see on the computer right in front of you is a perfect example of a 3D solid, where this part that we have here in front of us can be machined completely in a 3-axis vertical milling machine. And that's exactly what we're going to do. We're going to go through this step by step, and we're going to talk about importing a solid model. Importing a solid model sounds like a terribly dangerous thing, but it's actually very simple. We simply go to File, Import, and select the file type. Depending on which purchased options you have in GibbsCAM, you will be able to select different file types. The standard GibbsCAM solids reader will read in SolidWorks files and assemblies, parasolid binary, partition, and parasolid X_T or textile. It will do DXF and IGES, points list. There are a number of options in here that allow us to import options. And as you can see, I'm just going to grab this moving jaw and import it into GibbsCAM. Once we get it into GibbsCAM, we can move it into place, machine on it, and do whatever we want to. So importing a solid is not that mysterious of an action. I'm going to put that one in the body bag, and we're going to talk about this particular model, and we're going to talk about assemblies. When your part comes in, many times it comes in from an assembly, and it's not sitting in a vise in the middle of your milling machine. It may be on the 3rd floor somewhere in another subassembly. In that case, the model would not be anywhere near the main coordinate system. And by the way, let's review very quickly. Coordinate system 1 on your CS list is the anchor point of your machine, whether your machine is a vertical mill or a horizontal mill or a lathe or any other type of machine. It is the anchor point of the machine. And notice that when you open the CS palette, you cannot move it, alter it, change it, rotate it, or do anything to it. The first coordinate system is the anchor point of the machine, and X will always point to the right, Y will always point vertically, and the depth axis here will always point out of the tool. The tool will always go in through the depth axis, no matter which plane that you happen to be in. Now, let's look as if this model were brought in a strange configuration in another location. And in GibbsCAM, you do have the ability of moving a model simply by dragging it around the screen. So it may come in somewhere else, and we need to get it over here to the anchor point of the machine. So we have two questions. Do we take the machine to the part, or we take the part to the machine? Well, since the machine is anchored, we're going to take the part to the machine. And it can be as simple as we're going to go here to face selection. We're going to select this face. Since it's central to the part, we're going to right click on that face. And then on the right click menu, we have a functionality called Align Face to CS. When I click it, as you can see, it did align that face to the coordinate system. Now, I picked that face because it was symmetrical, and that's where I want the XYZ 0 to be. If I click this face, right click, Align Face to CS, it will align that face. We're going to back up a little bit with the Control Z undo, and we're going to see that the part needs to be moved. The top of the part needs to be moved down to Z0, which is where most of our parts are if you're here in the United States. If you're in Europe or other parts of the world, they put Z0 on the bottom of the part on mills and on the back of the part on lathes. I want to make sure that everybody can see my mouse okay. If I move it very fast, the mouse gets bigger, because I understand that sometimes the mouse is a little hard to see when we're doing a webinar. So I'll make sure I wiggle the mouse for you so that you can see it well. But for right now, let's move the top of this part down to Z0. We're going to do that using Absolute Translate. And if you'll notice up here on the top right-hand corner of my screen, I have created a custom menu that has my favorite commands in it. And one of my favorite commands is Absolute Translate. We're going to Absolute Translate in the Z-axis. I'm going to double click here, Absolute Z from, and I'm going to Alt click on the bottom of the part. Or should I Alt click on the top of the part? Depends on which dimension that I know. I know that's going to be 0. So it's at Z.5. I want it to go to Z0. I next click on the part, send the part to Z0. So bringing the part in from an assembly is a very simple task, and moving it to the XYZ home of the machine is also a simple task. Once you do that, you can add the proper amounts of stock that you want around the outside of the part. And as you can see, we've made this a fairly large billet piece so that we have some material to take off so that you can see some of the toolpath features of GibbsCAM. So how easy was it to bring a part in with import? It was simply File, Import, select your file type, select your file, and press Open. The file will come in, and sometimes it may way be off in space over here somewhere, but we can move it very quickly by right-click functionality of Align Face to CS, and you can also use the Absolute Translate command. Now, preparing the part for machining. We aligned this part to the coordinate systems of the machine, and as you can see, it's perfectly aligned with the X and Y axis. If it wasn't, if it were turned or skewed, we could extract geometry, find out what the angle is, and skew it back using 2D rotate. But I want to talk to you about something else that people don't know about solid models. When you import a solid model, and I get this question a lot, can I modify the solid model even though it came from another platform like SolidWorks or Inventor or Pro Engineer? And the answer is yes. When you bring a solid model into GibbsCAM, we are a direct solid modeling package. not a parametric-based package, which means that I can modify this solid model. In this case, we're going to perform an action that we commonly use. It's called defeaturing. If we wanted to make a particular stock body, and the stock body did not have this hole in it, I can remove that hole from the part simply by using a simple trick called defeaturing. We're going to go to the solid modeling menu. And from the solid modeling menu, we're going to select advanced solid modeling and then unstitch solids. I'm going to select heel only because I don't want to plug. Press do it, and the model has been defeatured. And as you can see, it is now still a single solid model, but the hole has been taken out of it. So we can modify solid models when we bring them in from other CAD sources. So the next question is, if I can modify that solid model, can I also measure that solid model in GibbsCAM? Because if you're not running spatial interop, and we will talk about spatial interop later, because it is available to SolidWorks and Unigraphics and Parasolid and Inventor, spatial interop will actually import a part with dimensions, but we're going to show you how to get the dimensions directly off of the part right now without extracting any geometry in GibbsCAM. We would like to measure this part. We would like to know how tall it is, how wide it is, what the radiuses are, so that we can plan our tool list. We certainly want to know what the hole diameters are. So we're going to use an interesting feature called Show Position. Show Position comes from the Plugins menu on Main Tools. And another tip, if you ever forget where a command is in GibbsCAM, you may go to the search window here on the top and type in the name of that command, Show Position. And as you can see, the Show Position command pops up. All we have to do is click on it. But there's something else that's very, very interesting. We have another little symbol here that says show me where it is in the GibbsCAM menu and show me where it is on a custom menu. So I'm going to click show me. The menu is going to open, and as you can see, show position flashes a few times. So remember, if you forget where a menu item is and you can't find it, you can simply go to the search area and search for that command, and it will show you exactly where the command is. So let's go back to the show position command for just a moment. If I click on the solid model and then click again, I can see that my H or X value where I clicked was this, and my Y value where I clicked was this, and my D value where I clicked was this. X, Y, Z translates to horizontal, vertical, depth. If you are on a 4 or 5 axis milling machine, as soon as you move out of plane, X, Y, and Z don't mean anything to us anymore, neither do G2 and G3. But we have HVD, X, Y, Z equals HVD, horizontal, vertical, depth. So now that we know how the show position indicator works and what the terminology is, let's start looking at the part at different dimensions. I want to get the dimension off of the top of this ledge. I'll click on it again, and the depth is minus 0.5. I want to know what the height of this ledge is. I will click on it, and the dimension is minus 1. Of course, the top of the part was 0. The bottom of the part, if I roll it away from me and click on it, you can see that the part is minus 1¼ tall. So that is HVD mode on the show position indicator. And again, this is very important for you because you have the dimensions right at your fingertips and you can proceed with machining right away. You certainly will want to look at your paper drawing that comes with your part because it tells you more about the GD&T the tolerances, and the method by which they want you to generate and tolerance the holes. They may want it bored, they may want it reamed, they may simply want it drilled. So let's move on to show position to mode number 2, which is thickness. We want to be able to measure the thickness of certain sections of the part. Again, because we're planning the machining process. And when we're planning the machining process, we need to know things like how thick is the part. If I click here, notice that a line shows up, and you can see that that line is 1 1/4 inches long. That is called the thickness indicator line. If I just click and hold my mouse, that's 3/4 thick from there to the bottom of the part. And from here to the bottom of the part, we can tell that that ledge is 1 1/4 inches tall. So the thickness indicator, which is mode 2 of the show position indicator, can help us determine the thickness of parts. Here, it's giving me the wall section from where I click to the other side of just that wall. It's telling me what the wall thickness is from here to the edge of the wall. And again, from here to the edge of the wall, or from here to the edge of the wall. Now, we have one more mode, which is extremely handy. It's curve mode. We get to find out what the radius of all of these holes are. And if it's infinite, it means that it's a complete circle. Here we have at the bottom, radius of 1875, 1875, 2-inch radius here, the diameter here, the radius here is 625, so these are 1 1/4 inch protrusions on the top of the part. So now that you know that you can use show position to machine your part, I'm going to leave it right here just in case we need it for reference while we are going to machine the part. Now, so that we have imported the part, we've brought it into place using several different methods, absolute translate and align face to CS. It's now time to set the part up on our fixture. And when we are fixturing parts, many times the fixture has items in it that we don't want to bump into. And fortunate for you, GibbsCAM has automatic fixture avoidance built into it. So how easy is it to put a fixture onto the part? It's as easy as going to our macro list, and there's a video that shows you how to download and install these macros. And I'm going to click a macro that I've already installed called 6-inch vise. And it's simply a Curt D688 vise. The macro menu comes up. I want to enter the grip distance of 0.250 down here on the bottom of the stock. Center the stock in X, press OK. And now we have a vise holding onto the part so that we can more accurately plan our process for top side, op 10, bottom side, op 20. And our fixtures may be more complex than this. But when you are able to bring in a fixture and plan your process around it with only a few mouse clicks, that brings tremendous value to your process and safety to your process as well, because process security is another thing that we're all about at GibbsCAM. We want to protect your investment in cutting tools. We want to protect your investment in machine tools and protect your investment in fixturing and the machine itself. So having the fixture there allows us to make our mistakes here on the computer before we send them out to the floor. Now this one's pretty simple, but as you can see, the vise is wrapped around the part. So we have analyzed the part for tooling selection, and I have created the tools ahead of time because I understand that most of you are very experienced and you don't need to see how to create a tool, but we have here a 2-inch face mill. We have a 1/2-inch high-speed machining end mill. An HSM end mill is used for high-speed machining. And in GibbsCAM, we have VoluMill licensed directly in our software. And the VoluMill license goes a long way because it is a tremendous product and it has revolutionized the way that we cut metal in the last 15 or 20 years. We've learned that instead of burying the end mill in the center using 100% of the step over, we use 10 to 12% of the side of the end mill step over, and we're able to cut much more quickly. And we're also able to cut more deeply with the end mill, which means that we're using more of the end mill and wasting less of it. So we have a high-speed machining end mill. What are the characteristics? Usually has no more than 3 times its diameter in flute length. It has 6 or 7 flutes, a 45-degree helix, and a special coating, usually, and in this case, today we are machining 17.4 pH with a Rockwell C of 38. So we're going to have ALTIN coating on our end mill to do the high-speed machining, ALTIN. We have a 1 1/4 inch semi-finish end mill, a 1 1/4 inch finishing end mill. We have a 1 inch spot drill. That's the insert drill. We have a 5/8 insert drill, and we have a chamfering tool for countersinking. So once we get the solid model in, do we have to extract all the geometry that we are accustomed to machining with to start machining on this part? The answer is no. And on this part, no geometry will be extracted. We will be able to do all of the machining directly on to the part. So let's get on with our first tool path. Let's go to facing, which is under the roughing. We're going to select face milling, and we're going to start at 20 thousandths and finish at 0. Our entry and exit clearance planes are 0.1 and 0.1. We're going to machine stock, one direction for best flatness. We're going to start in the X plus Y minus corner so that we throw the chips towards the back of the machine and put the force of the cut towards the hard jaw of the vise. Yes, we're going to use retracts. We're going to clear the cutter 1/2 inch from the side of the part, and we're going to use the new roll-in entry, which gives us a thick to thin chip on entry and exit so that we get a better part finish and a better insert life. Notice that we did not have to click anywhere on the solid to get this facing tool path. So let's go to OpSim and let's look at this tool path and see what we've got. We've got a piece of stock. We have a vise. Let's slow this down and watch this tool path that required absolutely no reference from the part whatsoever. It only required a reference from the stock body. So we were able to face the top of this part off, but all we see right now is the piece of stock. Wouldn't it be better if we could see the part inside of transparent stock while we are machining? Well, now I have the part as the stock is transparent. How do I make the part show up inside of the stock? I simply click on the solid model before I go into OpSim, and then I will see it inside of the transparent stock. Let's go to front view and let's zoom in on the part slowly, and we can see clearly that the stock, which is blue, is indeed above the part. And if we go to home view, no zoom, we can see that the stock completely covers the part with a little bit to spare. And now we can go and look at this tool path, which is a lot more meaningful to us now, because one of the first and huge advantages of machining with a solid model is that we can see it while we're cutting it. We can see if we made any mistakes. And yesterday, one of our best customers, I think he's with us today, I'm not going to mention any names, but his initials are Glenn Blake. He's an expert programmer, and he had a simple problem. He was using a quick geometry file, and he had a problem with it. I said, If you turn that into a solid, you'll find the answer very quickly. Well, within about 10 seconds, he knew the answer to his problem, and he was able to move on very quickly through the part. So here we are, we can now see the part inside of transparent stock. A tremendous benefit for you to be able to visualize the part inside of the stock. Don't you wish you could do that out on the machine? And you would know if you're anywhere near the part, or if you've left material on the part, or sadly, if you've cut material off the part. And of course, at GibbsCAM, we're going to do everything that we can do to keep you from doing that, which is why we have the graphical user interface for the first reason. For the second reason is to obviously to get out code, although that may be primary. So now we're going to grab the 1/2 inch HSM end mill, and we're going to select VoluMill. For those of you who are not familiar with VoluMill, it is quite simple. VoluMill is a new way of cutting. Instead of burying the end mill, we use a certain percentage of the end mill, and we slice the part with the side of the end mill rather than using the center of the end mill. We can cut much faster that way. We can cut much deeper that way. And you're going to see VoluMill in action right now on this solid model. The first thing that we need to do with Technology Expert is open it and set the material type, because VoluMill is twice as fast, at least twice as fast as conventional machining, and it gives you 4 times less tool wear than conventional machining. The RPMs and the feed rates are much, much faster. The RPMs are usually double or triple, and the feed rates are usually times 10 or times 20. But instead of you having to calculate all of that information, simply open Technology Expert, click your material, set your Rockwell hardness, set your machine taper, your max RPM, your max feed rate, and I always start with the workpiece holding slider bar right in the middle and the cutting aggressiveness slider bar in the middle. If you'll notice, while I'm sliding the workpiece holding slider bar, you will see the spindle speed and feed rate change. In this case, feed rate is changing, and cutting aggressiveness, speed and feed are changing. So I'm going to leave them both in the middle for right now, because I know this material very, very well, and we know what it takes to run this. Our toolpath type is VoluMill. We're using a hydraulic chuck because we need more rigidity when we're doing high-speed machining. The tool coding is coded. Well, guess what? Your feed, your speed, your depth of cut, and your step over have all been automatically calculated. All we need to do is click Apply All, and that's it. GibbsCAM and VoluMill have taken care of all of the speed, feed, and depth of cut for you. Here, we're going to set where the top of the toolpath is and the bottom of the toolpath. So I just type those numbers in by hand. Is there a way that we can get those numbers off of the workpiece? Well, there certainly is. We can double click. This is the top of the Z toolpath. We're going to double click in the top of the Z toolpath, and I'm going to alt click on the top of the part. And the dimension of the part jumped right into the dialog box. We're going to do the same with the bottom of the part. Where do I want the bottom of my toolpath to be? I'm going to tilt the part away. I have double clicked here on the bottom of the Z toolpath. I'm going to alt click, and the dimension jumps directly into the dialog box. And yes, we can do all of this in one cut. We can do all of this in 2 cuts. Right now, we're going to let it do 2 cuts. Use stock material only, climb, coolant for non-ferrous materials, and air for ferrous materials. We'll have a toolpath as soon as the process manager says that we have one. And yes, we do have a toolpath, and it's ready to go. If this is the first VoluMill toolpath that you've seen, you'll notice from the top that it looks like a bowl of spaghetti. because VoluMill was designed by a scientist and a mathematician. I'm going to show you that VoluMill toolpath right now, let you watch it run. Again, it's twice as fast and 4 times better tool life because we get to use more of the tool's depth, because in this case, we're only using about 10% of the diameter of the end mill. But one of the real tricks here is that we did not have to extract any geometry, no 2D geometry from the solid model. We simply clicked on the solid model and said, machine it now. So VoluMill, if you've never seen it run, it does work from the outside in on boss parts and from the inside out on pocket parts. I can change the depth on this case to 1.25 because we're going to machine this part from the bottom up. The process manager is done. We have a tool path on the bottom of the part. It is now time to machine any residual material that's left in this area. And since GibbsCAM has used stock and material only, we're going to change the depth of the tool path to the depth of the top of this little step right here. I'm going to alt click it, and yes, it is -1. I'm simply going to only clicked on the solid model. There's no geometry here. We're going to click do it, and we now have a material only cut, which you can see the efficiency of that around this step. Now, where do we leave material for this? Because we have XY stock and Z stock. Don't panic. We did not cut the part to 0 material because now we're on the solids tab and we're going to use surface stock. Whenever you click on a solid, the solids tab will light up, and then you can go to the solids tab and tell it how much surface stock you want to leave. That is global surface stock, X and Y. If you want to leave different amounts for X and Y, you may use X and Y stock, plus and minus, or Z stock, plus and minus. But this is considered a global surface stock here on the solids tab. So yes, we left 20 thousandths on all surfaces, both wall surfaces and face surfaces. So we've roughed out the bottom step, the middle step. Now we have a large area here in the middle that needs some work done to it. Can I reuse this operation? I certainly can, because I only need to change one parameter, and that is this right here. What is the depth of this roof from here to here? Double click here, alt click on the part, the dimension jumps in. We're still at use stock material only. We will let the process manager do its job. It's now complete, and we have a perfect 3-step toolpath working from the bottom up to rough out this part. Now, I'm going to put it on OpSim. I'm going to let you see some of it slowly at first, and then we're going to speed up as we get a little bit further into the part so that you can see how VoluMill works. Yes, we're going full depth at 10% of the width of the end mill, and the feed rate that we're using right now is 92.56 inches per minute on 17.4 stainless steel at Rockwell C38. Now, while you're watching this, you can save your technology. We're going to call this 17.4 VoluMill roughing. And I'm going to press save. And we just save that into our process library. The next time that we get a process with 17.4 pH stainless, all we have to do is right click, load process list, and go to the folder where we saved it. And you can bring that process back in, click on the part, and press do it. Now, notice that the part disappeared. If I click anywhere out here in space, the part becomes unhighlighted, and we need to highlight it so that we can see it inside. So now let's speed up through the VoluMill a little bit so we can watch how this part progresses. And yes, using saved processes can take a 5-minute development of feed, speed, and depth of cut and turn it into 5 seconds of feed, speed, and depth of cut. As in our last webinar that you attended, we talked heavily about saving tools and saving processes. And hopefully you're doing that and saving a lot of time. So here's the VoluMill first step around the bottom of the part. Now material only, the middle step on the part. And again, material only, the middle step on the part. So we are just about done roughing the part. We've got a couple of holes to drill. VoluMill is finishing up its job right now. Let's work towards drilling a few holes. I know that these holes are 5/8, and this hole in the middle is 1 inch. So I think it's time that we drilled a hole before we start semi-finishing the part. I'm going to take the 1 inch insert drill, select holes from the hole menu, and since it's an insert drill, we're just going to feed in and wrap it out. We're going to start drilling at 0 and finish drilling at -1.25. And again, where can I get that number automatically? I can get it directly off the part. If there's another number here and I want that number in there, double click here, alt click the bottom of the part. Now we do need to add a little bit for the radius of the insert. So I'm going to say -0.05 equals. Yes, remember that every field in GibbsCAM is a calculator. Add, subtract, multiply, divide. Okay, our level's 0.1. Flood is on. Let's, if we had through spindle, we would change it to through spindle coolant. It's time to select the hole to be drilled right now. There's no geometry here. And I can't simply select the hole because my do it light is not lit up. There's not enough information there. So when you get a solid model in, the next mind-blowing feature, and the reason that I use the word mind-blowing, and I know that's hyphenated, by the way, but the reason that we use that is because our customers tell us that when they see the profiler work, it literally blows their mind. So first, what is the profiler? The profiler is what we consider automatic feature recognition. We turn the profiler on here on the profiler control, and there are 4 modes: slice plane, slice spun body, if you're turning a part in a lathe, slice silhouette, if you have a part and you're looking at it from the top, and the silhouette is not contiguous. In other words, it's broken up at different points during the depth of the part. You can use slice silhouette to find that contiguous profile of the outside of the part and use the silhouette. But we're going to stick with slice plane. And what slice plane does for us, when we turn it on, I can drag it, and you can see it's interactive. It shows me where it is in the part. Well, I simply want to drag it down into that hole, and yes, the profile of the hole is now lit up. I select it, it's blue, and look, the do it light is lit. If I click do it, there's my drilled hole. Now we do want to make a little bit of a change here. We want to start drilling at -0.5. So we will wrap it to -0.4 and redo. That'll be a more efficient use of our time when we're drilling this hole. So the profiler can be dragged to any depth in the part. Now, does the profiler have any precision to it? In other words, can the profiler be set to a specific depth of known geometry on your part? And the answer is, of course, yes. On the profiler grid, that's where all the functionality is, the grid lines. We right-click the grid line, and I may set the profiler depth at minus 0.499. Apply. And as you can see, the two outer holes showed up, but that hole didn't show up because remember, its top surface is minus 0.5. So let's go to minus 0.501. And yes, we see all of the holes right now. So the profiler requires almost no work from you. It does not require that we extract any geometry from the part. Rarely ever do we extract geometry anymore, and especially on a solid model, because we can simply click on it. As you saw in our first 4 ops, we simply clicked on the model and said go, and GibbsCAM recognized what it was supposed to do. So automatic feature recognition here with the profiler. It's up here in the floating toolbar, and again, it has 4 modes: slice plane, slice spun body, slice silhouette, and slice cylinder. So we have drilled the first hole through the part. It's time to create the drilling for the other 2 holes. So let's bring the 5/8 drill down into the list. Go to holes like we normally would. The top of the hole. This is fun. We can get the dimension right off the part. The bottom of the hole, I think that number's fine. We better set this to 0.1 so we don't crash into anything. And of course, it's an insert drill. Doesn't require any pecking. I may now select both holes with my control key and click do it. Without extracting any geometry from this solid model, we have, let's slow this down so we can watch the drilling. We have roughed and drilled the holes in this part. So let's see, let me go to my checklist and make sure that we've done all the objectives. Transparent stock, fixtures, and custom stock. Yes, we'll talk about custom stock in just a moment. Analyze cut part. Here's a new one. When we go to machine a part, a very complex part or a very simple part, if we're in OpSim, there's a little button right over here on the OpSim control bar called Analyze Cut Part. And this is an indicator that doesn't require you to pick up a micrometer or to interrogate anything. It simply tells you if there are any undercuts on the part body, undercuts on the cut part. And as you can see, it is shaded red. And we know that shaded red means that we are right on the surface. If it were solid yellow, we would have left material on the surface. If it were solid red, we would have cut material off the surface. So now let's click on remaining material on the part body. So because we have an accurate solid model, we can see where we have left material on the body. We've left material on the chamfers, on this face, on these 2 bosses, and on both of the outside profiles. The holes, if we click remaining material change, the holes and the top surface of the part are complete. Anything that's green is complete. So this analyze cut part, this isn't just a little toy. It is a tremendous tool that can tell us if we have violated the part, or if we've left material on the part, or if we have remaining material change. Now, if it's a 50-cent part, it's not a big deal. But you probably have parts that may be in the thousands or hundreds of thousands of dollars. And you want confidence that you have not overcut or undercut that part, that you have done your job exactly like you need to, and you have no fear of scrapping the part because we have used Analyze Cut Part. Again, it requires no tools. It requires no tools. Just have a look at the parameters that are on the Analyze Cut Part, select which one you want. Now, we all know about machining. I'm going to do one more contour pass, and then we're going to move to another part very quickly. So one more contour pass I'm going to do with the 1 1/4 inch end mill to show you how contouring works on solid models. I'm going to turn the profiler off. I'm going to set my contour depth at, why don't we grab that right off the solid model? And we need an entry and an exit. We're going to leave 0 stock on the part, and we're going to turn cutter radius compensation on. It's time to machine the outside of this part. If I click do it right now, I've only selected the part itself. If I click do it right now, ladies and gentlemen, we have a tool path around the outside of that part, no geometry required. Watch what happens when I change the depth. I'm going to alt click here on this ledge, and I'm going to simply click do it again. GibbsCAM recognized the material at the new level. I'm going to change the material again to -0.5 and press do it. And since it is smart, it only got one of those. It wasn't quite sure of our intent, but using the profiler, I can drag the profiler up into the part, click here, and look at what we get now that the profiler is on. We get our machining markers that we're very familiar with, but there's something missing. We don't see the inside, outside, and center circle. We only see the machining markers. That's because GibbsCAM understands the difference between a boss and a pocket. And let's take off ramp down. That would probably make a better tool path, wouldn't it? Ramp down, we'll get rid of that. So there we have used the profiler for one and the solid for the other. So I wanted you to see how this works with the profiler. Now, let's move on to the next part. We have another part we want to look at, and we're looking at the clock. We have a thing here called the flange part. And we're going to talk about this part, not from a machining standpoint, but from a, of course, I open the flange part again. Let's go to slot block. We're going to talk about other benefits of having solid models, not just a solid model of the part, but a solid model of the machine itself in machine simulation. And it can be extremely handy for us. Here we have a Haas VF6 with a 210 size rotary table on it. It does have a riser block under it. And when we set this part up in the machine, in machine space, we want to know if everything fits. One of the advantages of having solid models and machine simulation is that we can check to see if this part and the fixture that it's going to sit on will fit inside of the machine, and we'll be able to rotate to all of the angles that we need. So I'm going to rotate the A-axis, and it appears that we just missed. Oh, there we go. You can see that we would need to design the fixture with the part a little bit higher up in the air. So we can go to document control. And if you've ever wondered what this number was right here, I'm going to change that to 6 inches. And you'll see that the part is now moved upwards 6 inches from the top of the part to the center of the part. And we can check for clearance again. Yep, we still have a clearance problem, but in this particular part, we're only machining on the 45s. So if I go to the A-axis and type in 45, I can see that plus 45 looks good. And I can type in minus 45, and minus 45 looks good. And I can even lower the part back down to where it was before. Check the angle one more time. And there we go. We know the part now fits in the machine. So with solids, another advantage that we have is that when we want to create a new coordinate system to machine this face and this side, it's a very simple matter. Let me run this, run a little bit of this tool path for you so that you can see what's going on. And then we will stop for a minute and go back and see how we created those coordinate systems. Yes, I'm kind of going through it a little bit quickly. We're going to slow down. And yes, when you are machining in different angles, GibbsCAM understands material only in this simple facing cycle. And we can check and make sure that the machine is doing what we want it to do. GibbsCAM is automatically checking for collisions to make sure that this doesn't hit that. If it did, you would get an indicator that would say collision detected. But let's go back and look at how do we create a coordinate system for this machining surface. That's one of the other tremendous benefits of machining from solids. We don't know what the angle of that surface is. We may be reverse engineering this part and we may not even have a paper drawing, but I want a coordinate system from that face right there at that angle so that I can machine on it. So what do? I turn on face selection. I select that face, and then on the plugins menu under solids, you will see a command called Auto CS Create. I have one up here in my favorites. Auto CS Create. Create the CS origin at face corner or at the part origin. Let's do it at the face corner. We go to our coordinate systems list and look, Auto Coordinate System has created a CS right there. We can go home and start machining on it right away. So right away, the setup of this part, the cost for you has been dramatically decreased because you're able to get the information directly off of the solid model. And this is what this story is all about. What can solid models do for you? They give you a much better picture of the part. You get to see things that you may not see on a very complex 3-view or 4-view or multi-page drawing. We get to see it right here on the screen. We get to select the machining dimensions directly off of the part. We get to use the show position indicator and measure the part before we ever even place our first cut on the material. So this is about how we can benefit your company and what we can do for you. And I think it's time for Mr. Bart. Mr. Bart, would you like to come in and say a few things? Is that correct?
Yeah. Hey, Patrick, how you doing? Thanks for doing the presentation and showing us all the many advantages of using solids to machine your parts. So what I'd like to do is open up the floor. If there's any of the attendees that would like to ask a question, just type it down there in the chat area, in the questions area, and we'll address it. Now, there has already been a couple submitted, so I'll address one of them. One of them was, is CAD modeling included with your CAM software? And the answer to that is yes. And not only is the CAD modeling capabilities included with the software, but it's what we specifically call CAD for manufacturing. So in other words, we have CAD in our CAD capabilities and solid modeling capabilities in our software, but they aren't intended for like design engineering of a part. It's CAD capabilities and modeling capabilities specifically for what you need to do on the manufacturing side. For example, Patrick showed you the ability to defeature a part. There's many times you'll get a part that has features on it that you don't want in the way while you're machining the part, so we can defeature the part. Or another thing is he's showing you here, the CAD modeling allows you to set up machine simulation. Don't see just the tool cutting the part, but see the entire environment of what's going on in the entire machine. These are all advantages of solids, machining with solids. Let's see. Do we have any other questions? Yes, we do. Let's see, this question is, what are the different levels of solids? That's a good question. GibbsCAM comes in 3 different levels of solids. The first level is what we call solids import. It's the ability to read in the solids, but once you read it in, you can't do anything else with it other than subtract geometry, extract geometry from it, and then you can machine it just like you do if you're not using solids today. The next level is exactly what Patrick showed you today, and that is 2.5D. 2.5D solids is just a fancy way of saying prismatic parts. Okay, flat walls, vertical walls, round holes that go through it vertically. With 2.5D solids, you can not only read in a part in many different solids, You can read it in, but you can access, you can touch that solid. You can do things to it like Patrick showed you. You can click on faces and move it into position. You can extract features. You can start with a blank screen and model a part. And that's on the modeling side. And on the machining side, you can machine directly on the solid. You do not need to extract geometry like Patrick showed you with the profiler, or just click on the solid and say rough it. These are all the advantages of using solids. And then finally, the third level of solids is 3D. As Patrick mentioned, this is when you start getting into non-prismatic parts. This is when you start getting into organic parts that have swept surfaces, and you need ball end mills to surface those faces. So GibbsCAM comes in 3 different levels of CAD solids, or in solids. One of them is purely reading capability. The other 2 allow you to create models, modify models, and machine directly on the models. So, and I'm looking to see if there are any last questions. Let's see, would I need a post upgrade to use solids? Another good question. That really just depends upon the application. So for example, the first part that Patrick showed you earlier, the flange part that he showed you, no, you wouldn't need a post upgrade for that. But for this, what you're seeing here, this 5-axis, yes, you would need to have a post upgrade to support that. Post upgrade isn't dependent upon solids. Post upgrade is dependent upon the application in the machine. So, and let's see if there's any more. That looks like all the questions. Patrick, did you want to expand on any of those answers that I just gave? If not, we'll wrap it up.
No, you did a great job. Thank you very much.
Sure. Well, to close this up, because I realize we've gone longer than the time that we had originally scheduled, I just want to say, you know, hopefully you've seen here while Patrick was doing this demo, there are many advantages to using solids for your machining, not just on the CAD side, but on the machining side as well. Right from when you read the part in, to positioning it, to prepping it for machining, to when you're generating toolpath, a lot of advantages to a solid, all the way to final simulation like Patrick is showing you here. So there's a lot of advantages. And if you don't feel that you're using solids to their fullest extent right now, just contact us and let us know, and we can talk to you about how you could be using solids, whether you have them now or not, how we could use them to help you increase your part programming time, increase the proficiency of the machines, and as Patrick put, you know, increase your bottom line, your profitability. So with that, we will end this webinar, and we just want to thank everybody for not only taking the time to sit in on this, but knowing that we went over our time. We really appreciate you sticking out and staying with us. So contact us if you have any questions. Keep an eye out for our monthly tech tips, and we will be doing another webinar in the first quarter of next year. We're going to move to a quarterly webinar format. To that, we'll say goodbye to everybody, and thanks for attending.